Yeah, welcome to a short excerpt in Catabolism, groups and principle. You want to understand how the things are functioning in catabolism? Here we go. If you metabolize carbohydrates, every time the same thing happens. And if you have understood the basic principle, what is happening there, and over the groups, what is a carboxyl group? What are oxidation stages? How can I come up with a name as 2-keto 3-desoxy phosphogluconate? And you can deduce a structure formula out of that. What is a dehydrogenase doing, and so on. And if you have understood a couple of these basic principles, these are not many, then you basically have understood everything about sugar metabolism, and this makes life way easier. So here we go. To begin with, it should be clear what we're talking about. We talk about catabolism of sugars, so carbohydrates, and this is what we restrict ourselves to. And if these are carbohydrates, we have just three elements there. It's carbon, it's oxygen, it's hydrogen. And this simplifies things a lot because, let's say, the chemical variety we are talking about is very simple. So let's first have a look in what groups are we talking to. And at the end, you remember, it's always about bringing energy in, at the end, oxidizing it. Catabolizing means always oxidation at the end. And what actually happens there to oxidize it. That's the first thing we want to have a look at. So groups and principles. Let's start with I would say, simplest group in metabolism. This is a methyl group, obviously. We now oxidize this group, and the next group it's an hydroxyl group. Let's make it like that. And of course, this group here is termed hydroxyl group. Okay. Now, if we go one step further, we have this group, and of course, this is an aldehyde group. And finally, this group, I put a CH2 here, I will show you immediately. This is then a carboxyl group. This is, of course, the acids. This is a carboxyl group. This is a carboxyl group. And the whole group here, you term an acetyl group. Okay, and finally, of course, we have carbon dioxide. And one group we put just under the aldehyde group and this is of course then a keto group. So these group names are really essential to know. These appear thousands of times in catabolism of sugars. And these are the groups you expect to have at sugars. And of course, you should be able to name them, because this is if someone talks about something is happening at an aldehyde group, of course, you should know how this aldehyde group looks like. So, but it's simple because you have just this handful of groups you need to know. And that's it if we talk about catabolism. So sugar catabolism, as we only have carbons, hydrogens, and oxygens. So we have the methyl group, hydroxyl group, aldehyde group, carboxyl group, and the keto group. So if you name such a substance, this substance will be called an ol because it's an alcohol. This substance is an aldehyde. So this at the end, you will have an aldehyde. This substance will be an ate at the end. And this substance will be an one. So this is ethanol or glycerol. This is glyceraldehyde. This is glycerate. And then you have a carboxyl group. And you have here, for example, dihydroxyacetone. And then you have this own at the back. So you see already based on the name what functional group is there. If this is the single functional group, of course you can have more than one functional group. And you are aware that a sugar always will have an aldehyde group or an keto group and an hydroxyl group. So a sugar is this plus this. Yeah? So this is a sugar. Okay, now the interesting thing is, you see there is more oxygen. So you remember oxygen is, it looks like it's more oxidized if there is more oxygen. And you remember oxidation is loss of electrons, reduction is gain of electrons. So let's look at the oxidation numbers. And the oxidation numbers can be simply calculated in an organic substance just based on the electrons which are attributed to the corresponding carbon. Let's start with the carbon here. Let's start with the methyl group. So if the higher electronegativity gets all electrons. We here talk only about carbon, hydrogen, and oxygen. So the highest negative electronegativity is O, then we have carbon, then we have hydrogen. So if there is a carbon and a hydrogen, the electron goes to the carbon. If there is a carbon and an oxygen, the electron goes to the oxygen. And of course the same is true for hydrogen if it's bound to oxygen. We only look now at the electrons of the carbon. So carbon, of course, is 4 valence. So we have 4 valencies. There can be 4 electrons at maximum, which are attributed. So maybe we start here with the first one, which is methane. So methane could be here. So just for the sake of completion. And of course, this is 4 times minus 1. So it's minus 4. So we are here at minus 4. Now, this is just for the sake of completion. Now, the methyl group, this is R always is a carbon. So here we have a carbon. So it's in this case 0 because the carbon-carbon bond, of course, the electrons are not attributed to a certain carbon. And this is 3 times minus 1. So in other words, this carbon, the oxidation number is minus 3. Let's go to this group here. We now look at this carbon. So in this case, we still have 2 hydrogens. So it's 2 times minus 1. And then it's plus 1 because this electron here is attributed to the oxygen. So therefore, we have a plus 1 here with respect to the oxidation number. And of course, in sum, this is minus 1. So this carbon has an oxidation number of minus 1. Now we go to the next carbon here. So maybe here I add another methyl group and then the rest. Then it looks like the others. Okay, so let's have a look at the carbon here in the aldehyde group. So again, we calculate it is minus 1 for the hydrogen. Now we have 2 bonds with the oxygen. So it's plus 2 times 1. So therefore it's plus 1. So here we are. So this carbon has an oxidation number of plus 1. And then we go to the carbon in the carboxyl group. This carbon here. So we count 3 bondages to oxygen. I always neglected, of course, we always have another bond to the C, but this is always 0. So we have then 3 times plus 1, and this is of course plus 3. So this carbon has plus 3. And obviously in the case of carbon dioxide, we have 4 bonds to oxygen. All electrons are associated with the oxygen. So therefore this carbon is plus 4. This is the highest oxidation number. If we look at the keto group here and we have a look at this carbon, let's first check this methyl group here. So here we have 2 times minus 1. The carbon bonds here and here, here and here. It's a carbon bond, so this is of course 0. So this is then minus 2. Minus 2. And now let's see how this is for this keto group. And there we have 2 times plus 1, because we have 2 bonds to oxygen, plus 2 times 0, the carbon bond, so it's plus 2. And this methyl group, of course, we can just copy. This also has -3. So now if you would add up the oxidation numbers of these 2 groups here, let's do it like this, -3 plus 2 is equal to -1. So in total, the oxidation number of these 2 groups is -1. If you do the same with your aldehyde group here, and it's +1 minus 2, it's also equal to -1. So you see overall, there is no change of the oxidation numbers if you look at these carbons. So if you just move this keto group here to this position, of course the oxidation numbers of the carbons where you have this double bond O change, but the overall oxidation number does not change. So overall, if you just move keto groups, or in this case aldehyde to a keto groups, there is no change in the oxidation, and you know an enzyme doing this is called an isomerase. So an isomerase simply shifts or moves keto or aldehyde groups. That's everything, and this is not an oxidation. You see that there is no change here. So at each time you see an isomerization, no oxidation is happening. If we go from here to here, or here to here, or back, or here to here, or back, but I put the forward reaction because this is then the name. This is always a dehydrogenase. And of course also this is a dehydrogenase. This oxidizes. And also this is a dehydrogenase. And of course, as this is an oxidation never comes alone. So if you would go from there to there, you will have to produce an NADH or NADPH. That doesn't matter. So there you will have the production of NAD. I put here the P in parentheses, H, and the same here. So you need to couple that, NADH. So if you have a dehydrogenase, you must have at the same time the production of a molecule like NADH. If this is an oxidation like here, and it's likely to be an NADH. If it's another oxidation, you remember in the citric acid cycle, we have succinate to fumarate, where we just create a double bond. That's also an oxidation. But there the redox potential is not high enough. There we only produce an FADH. But here, in general, if you go from a methyl group to a hydroxyl group, if you go from a hydroxyl group to an aldehyde group or to a keto group, and if you go from an aldehyde group to a carboxyl group, you would expect, first of all, it is an oxidation. Therefore, the enzyme is termed a dehydrogenase. And second, you would expect that an NADPH or NADH is being produced. Of course, always an NAD plus molecule gets in. I didn't depict that here. So this is what the basics of the groups, the enzymes which shift between these groups. If you change the oxidation number, of course, the enzyme is an enzyme which oxidizes, and this is called a dehydrogenase, and you have an NADH. And if you shift your keto groups, this enzyme is called an isomerase. Now we have talked about groups, let's talk about links. So let's put an 8 in the middle with a carboxyl group. So this is an 8 because it's an acid. If we add now an ol, which is of course an alcohol, R2CH2OH, this is an ol, of course. And if this reacts with an 8, we don't care about the water leaving, we get this. And this is an ester, because it's an ester bond. This is an ester bond. And you remember, this is not energy rich enough. And the energy of an ester bond is not energy rich enough to be transferred to ATP in substrate level phosphorylation. Now what's happening if I use this substance here? This is a thiol, because we have an sulfur instead of an oxygen. And if this reacts with my carboxyl group, I get this substance, thioester. And finally, if I have a phosphate reacting and the phosphate reacts with my 8, the phosphate is an acid and the 8 is an acid, and of course I get then this molecule here, and this is of course then an anhydride. This is if two acids are bond, and this is an anhydride. So these are the principal bindings you see in catabolism. Of course, in organic chemistry, you have learned way more, but these are the ones you should absolutely know. If an hydroxyl group reacts with an acid, it's of course an ester. If phosphate, which is an acid, reacts with the carboxyl group, which is an acid, this is an anhydride. In this case, it's a phosphoanhydride. And if a thiol, which is kind of an ol, just with a sulfur, if a thiol reacts with an carboxyl group, you get a thioester. These are the basic things, and you know that this molecule, the energy is enough for a substrate level transfer on ATP. By the way, if you have the glycoside linkages, these are two hydroxyl groups and you split off water, and then you have an glycosidic linkage. And of course, sometimes you also see ether linkages, but this is rare in catabolism, which is a COC linkage. Okay, this just for the sake of completion with respect to the groups. Now we talked quite a bit about the central groups and what happens if these groups react. We have seen that isomerases just move these keto groups, and we have seen that the dehydrogenase oxidizes. But you have learned about oxidation, and an important reaction is a decarboxylation. So if a carboxyl group leaves in carbon dioxide, and it's often confusing when is this now an oxidative decarboxylation and when it's just a decarboxylation. So let's just look at pyruvate and look in detail to understand when it's what. Here we go. Okay, so let's start with the molecule of pyruvate, and of course you remember that it has 3 carbons. So this is of course pyruvate. And if we now look at the oxidation numbers of the carbons, we have here a methyl group. We know this is -3. We have already counted for the keto group that this is +2. And we have also counted for the carboxyl group before that it's +3. It's just 3 times +1, 3 times +1, 2 times +1, and 3 times -1, and then we come to these oxidation numbers. Now what happens if my carboxyl group leaves like this? If I get a carbon dioxide and the remaining molecule is acetaldehyde. So let's just put the oxidation numbers, because what we want to see now, is this an oxidation at the same time or is there nothing happening? Of course, I cannot just look at the molecule. I need to look then at the oxidation numbers of all carbons, because if there is an internal shift, nothing of course happens. We have seen that with the isomerases. So of course at that methyl group nothing changes. It's still -3. This is now a aldehyde group here, and we have already calculated, but we can of course recalculate it. It's -1 plus 2. So therefore it's +1. And you might remember carbon dioxide, we have of course 2 oxygen molecules which are bound with 2 double bonds, so it is +4. So in total, if we calculate all the oxidation numbers, we have at pyruvate +2 with respect to the carbons. And if we do the same here, then we have also +2, -3, +1, +4 is +2. So therefore it's no oxidation. So therefore this enzyme is called pyruvate decarboxylase. This is just a decarboxylation. It's not at the same time an oxidation. Now what happens if I go like this? If I again have a carbon dioxide, now I have here a carboxyl group, CH3. This is of course acetate. And if I put now my numbers I have here again at the methyl group, nothing has changed. This is -3. At the carboxyl group, it's +3. It's 1, 2, 3, fold 1 +3. And here it's +4. So here I have now altogether -3 +3 +4 is +4. Therefore, this is an oxidation. So this is an oxidative decarboxylation. And this is catalyzed by the pyruvate dehydrogenase. In reality, you know, of course, first of all, we produce NADH. We cannot do an oxidation like this. And second, we have also the coupling of CoA, and this is then also a TO-eder. So we have in total this reaction, but I wanted to show you what's happening here at the position of the carbon, that you see this oxidation. So we form also a TO-ester to conserve the energy, and we have, of course, as it's a redox reaction, at the same time NADH production. So this is what's happening at the level of pyruvate. So these two forms we have, a decarboxylation when we have no oxidation of the molecule, or an oxidative decarboxylation when we have an oxidation of the molecule. And then of course the enzyme doing that is called a dehydrogenase. And you remember that happened quite a bit in the citric acid cycle. And in the citric acid cycle, it's not necessarily the group directly at leaving group which is being oxidized. This could also be the group at a position 2 or 3 if there is a hydroxyl group, which then is a keto group. So you just to see it at the end, you would have to count all carbons, the oxidation numbers of all carbons where you have a change to be sure. But normally it happens directly at the position or at the next carbon where the leaving group was bound, and then it's quite straightforward. So you see, this is a straightforward possibility to check whether we're talking about an oxidative decarboxylation or just a decarboxylation. And if it's an oxidative decarboxylation, you name the enzyme in general dehydrogenase, because you always name enzymes dehydrogenase if they oxidize. It could also become from the reverse reaction, but that's something we don't think of now. And if it's just a decarboxylation in general, you would name this enzyme decarboxylase. Of course, always in general, not all enzymes then are named like this. Now we have talked about groups. We have talked about redox reactions, simple redox reactions where we simply oxidize an hydroxyl group to an aldehyde group or keto group, and finally an aldehyde group to a carboxyl group. This is the sequence of oxidation. We have seen how we can decide whether a decarboxylation is just a decarboxylation or an oxidative decarboxylation. But the other problem with all these molecules is often the names are sometimes confusing and they look so long and look so ugly. Of course, for sugars, unfortunately, there is no rule of thumbs, because for a sugar, as soon as the keto group has moved or a hydroxyl group is another site at another position, the name of the sugar is different. So there is no, let's say, rule of thumb how to help you with the names of sugars. Therefore, I don't expect you to know names of sugars, with the exception of glucose and fructose, and these you also need to be able to draw. All other sugars, there are tons of other sugars, all with their own names. This is just learning by heart, to be honest, because there is no clear link from the name to the sugar. So what we talk here is just things which makes sense. Now, I started talking about a sugar. Now, and we have already learned that a sugar is always a reducing group, an aldehyde group or a keto group, and at least an hydroxyl group. That's the definition. Otherwise, you're not a sugar. So now let's have a look how glucose looks like. This is, of course, something you know by heart. And then we deduce based on glucose how the structure formula of a complicated molecule, complicated sounding molecule in the Entner-Dauderoff pathway looks like, namely 2-keto-3-desoxyphosphogluconate. Here we go. Before we go to this complex molecule, we start with more simple molecules in the glycolysis. You remember on the C3 level, we just talked about two names. It's all about glycerol something, and it's dihydroxyacetone something. If you know, acetone is a C3 substance, and you hear in the name it's an one. Therefore, you already know that if it's an one and it's C3, the only way to put the keto group is at position 2. Otherwise, it couldn't be an one. There is no other place. If it would be at the end, this molecule is an aldehyde. So it's no more an one. So therefore, you cannot term it one. So this must be an one. If you don't know what acetone exactly is, it doesn't matter. The molecule is called dihydroxyacetone. In general, two hydroxyl molecules at the same carbon you will rarely see. This is not stable. So therefore, dihydroxyacetone means that you have to have a hydroxyl group here and a hydroxyl group there. And of course, now we have to fill it with our hydrogens. And this is indeed, so based on the name already, if you know it's a C3 substance, you could construct it, even if you don't know that acetone looks like this. This is acetone. It just has then two methyl groups. This is acetone. And this is dihydroxyacetone. So that's it. So you know based on this that this must be dihydroxyacetone. Now, the other molecule we have in the citric acid cycle was glyceraldehyde 3-phosphate, which was our central molecule. Now this comes, of course, there the starting molecule is glycerol. So, and glycerol, this is of course something you were allowed to know from your biochemistry lecture. Glycerol, or from your organic chemistry lecture, glycerol looks like this. So it's also a C3, and it has hydroxyl group at each of these C's. So this is H2C, HC, H2C. So this is glycerol. If I put an aldehyde group here, then I have, it's still the glycerol backbone, glyceraldehyde. So it's derived from glycerol and it's called glyceraldehyde. All the alcohol, aldehyde, in this case even the sugar. And we have learned before an acid is an 8, and if I put here a carboxyl group. This is glycerate. So this glue stuff all comes from this glycerol. This is derived from this. And now you could say, if I have this molecule, so this molecule you see here, the difference is that my hydroxyl group here is missing. So I could name that 2-desoxyglycerol. So a molecule which is named desoxy just means that at this position I have removed an oxygen. So if you know that glycerol has 3 hydroxyl group at all positions here, then obviously and desoxy just means that I removed at the C2. In this case, it is very simple. The numbering goes from both directions. It's the same. It must be the C in the middle. I just removed an hydroxyl group. Whether you would name now this molecule 2-desoxyglycerol is a matter of debate. Of course, you could also name it propan 1,3-diol. That doesn't matter, but it's not wrong to name it 2-desoxyglycerol. You could also name dihydroxyacetone. You could also name it 2-ketoglyceron, or you could even name it glycer2-on. This is also not wrong. So that would be also a correct name. Yeah, so this is just the naming, and this is how you can deduce the molecules based on the name. This works good in the glycolysis because there basically you just have this glycer stuff. This works not so good in the citric acid cycle because in the citric acid cycle, unfortunately, each new molecule has a new trivial name which you have to learn if you want to learn the citric acid cycle. So there, each molecule has its own name, and that's often the case that, let's say, famous metabolites have their own name. But, and I said we come now to this famous large molecule of the Entner-Doudoroff pathway. We start with glucose. For glucose, of course, the first thing is, if you want to write it in the Fischer projection, you have to distribute your hydroxyl group at the correct positions. Ta, tu, ta, ta. So this is glucose, and of course here I have an aldehyde group, and of course I shouldn't forget the hydrogens, and here I have a hydroxyl group. This is the glucose. If I oxidize an aldehyde group, you remember this is an enzyme. The enzyme which is oxidizing an aldehyde group is a dehydrogenase. So, and if I oxidize an aldehyde group, I will get a carboxyl group. So if I oxidize that, I will get this molecule. And this is gluconate. It's an 8, it's an acid. At the position 6, I start counting also always from this C here. This is position 1, so this C down there is position 6. If I have a phosphate here, this is 6-phosphogluconate. So, and you remember, this is the first step, the second after the kinase has phosphorylated the glucose. This is the first step happening in the pentose phosphate pathway, heterofermentative lactic acid fermentation, and in the Entner-Doudoroff pathway. And in the Entner-Doudoroff pathway, then I have a molecule which is called 2-keto 3-desoxy 6-phosphogluconate. This name sounds like hell, but you can simply read it like it is. So you see it's 6-phosphogluconate. So we just copy first of all this 6-phosphogluconate molecule. We start with this. So let's put a 6-phosphogluconate molecule first. So now I just read it. I start with 2-keto. So C2 is here. This is my C2. So I put a keto group here. That's the first thing to do. And at position 3, I have a deduce. So therefore, deduce means that the hydroxyl group is removed. Instead of the deduce group, I have now just an hydrogen. And you see, this is 2 keto, 3 desoxy, 6 phosphol, gluconate. And just based on applying step by step these groups. So some things, of course, you need to remember forever. Otherwise, you have no chance in the glycolysis or other catabolic pathways. This is, of course, you need to know how is glycerol looking like, what is acetone, and then you know if it's dihydroxyacetone, you know how it's looking like. If you have glyceraldehyde, you can deduce it, and of course the glyceraldehyde 3-phosphate, it's also easy. You always start counting from the aldehyde or carboxyl group, and then you can deduce all other things. You need to know, of course, the structure formula of glucose in the Fischer projection and in the ring form. And if you know that, then also you can deduce gluconate because you know an 8 is an acid. So if you really have these names here in mind, if you know that an one is a keto, has to have a keto group, an aldehyde obviously has to have an aldehyde group, and then everything is fine. You can deduce almost everything based on the structure formulas in sugar catabolism. Of course, things get a bit more complicated if you have then nitrogen, sulfur, and so on in, and if you have then catabolic pathways with amino acids or things like that. But we talk about sugar catabolism at that place. So if you have these principles understood, if you know what group people are talking about, you should be not in fear about the catabolic pathways. We have, of course, talked about enzymes, and we have talked about isomerases, dehydrogenases, and so on. Maybe, once again, let's summarize how these enzymes can look on one scheme. Okay, this substance X is certainly a substance you will never see in nature, but we don't care. I just want to use this substance X to demonstrate some of the key enzymes you have in glycolysis or in general in catabolism of sugars. So this substance X, you see, we have a couple of groups, and an epimerase, you know, this changes hydroxyl groups. So it could change the hydroxyl group to another position, or I can just move it, and you see here with the epimerase we have moved this hydroxyl group to another position. So if you see these two molecules, you know in between must be an epimerase, and this will be then called substance X epimerase. An isomerase, you know, you move aldehyde or keto group. So here we have a carboxyl group. This is the only keto group to move. So the only thing we can do is move this keto group from the C2 position to the C3 position. Voila, here we are. Usually that's always with a hydroxyl group. I removed that here, but it's just to demonstrate what's happening. This is an isomerase. Here we have a dehydrogenase, and I said enzymes can be named after forward or reverse reaction. Isomerases, you remember, these reactions are can go in both directions. The same is true for epimerases. So, but also dehydrogenase in general, depending on the reaction it's catalyzing, might go in both directions. And in this case, so we have named it from the reverse reaction. So in this case, this hydroxyl group is being oxidized to get substance X. And of course, if we call this then, if this is substance Y, this enzyme would be called substance Y dehydrogenase, because I oxidized this hydroxyl group here. And of course, if I go back, then I will produce NADH. And in the case I go in this direction, I will use electron equivalence to reduce this keto group to an hydroxyl group. So this enzyme is just named after the reverse reaction. And this is, of course, in this case, in this direction, a reduction. In this direction, an oxidation. Kinase phosphorylate. So this is again called in this case after the reverse reaction. So here, if we phosphorylate this hydroxyl group, this with ATP, this would be called an kinase. So also this reaction is certainly reversible because we have here a carboxyl group and phosphate. So this is a phosphate anhydride bond. We have enough energy to transfer that onto ATP. And if we would go in the back reaction, this would be called a kinase. This is not a phosphatase because a phosphatase splits away an inorganic phosphate. So also named after the reverse reaction. Now, if we go further and we have a decarboxylase, you remember in this case, if we just allow the CO2 to leave, then this electron comes to the carbon here. So in this case, you would expect, like in the case of pyruvate, to have an aldehyde group which is remaining there. And exactly that's what we have. So the carbon dioxide leaves and we have an aldehyde. So this is a non-oxidative decarboxylation. An oxidative decarboxylation, then this at the same time would be an oxidation here. So we would have then a carboxyl group at that position and carbon dioxide here leaves. So this is in summary, let's say the key enzymes you have in sugar catabolism. Of course, you have also others. You remember in glycolysis, we have mutases, we have enolases, and so on. So, of course, you will need a couple of more. Transcatalases, we have talked in the pentose phosphate pathway, but these are the key enzymes. It's important that you have understood the principles, what these enzymes are catalyzing. And then if you see a reaction, you already know what enzyme is doing it. Or if you hear that this is a dehydrogenase, you could almost be sure if this is the substance you're starting with, that of course this is the only carboxyl group which can leave. Then in 99% of the cases, you will have an oxidation at that position. Yeah, thank you for your attention. Now you have understood what's behind. And now if you go now and watch how glycolysis works, how a fermentation pathway works, everything is clear. Welcome and goodbye.